Hello everyone, and welcome to today's webinar, Leveraging Kubernetes Services and DNS. I am pleased to introduce today's speaker, Christopher Lilienstope. He is the original architect behind Tigera's project Calico. And he speaks at a ton of meetups every year, educating people on networking and network security for modern applications. He also consults with Tigera's enterprise clients on their security and compliance for modern applications, and especially on Kubernetes, Istio, and all of those kinds of things. So before I hand the webinar over to Christopher, I have a few housekeeping items I'd like to cover. First off, today's webinar will be available on demand almost immediately after the session is finished. It just takes time to process, about 5 minutes, and then it's available. And it is available through the same link that you used to get this webcast. And also, we'd love to hear from you during today's presentation. So we will have a Q&A session at the end. But if you have questions, please go ahead and enter them into the question bar on the BrightTalk interface when you have them, and we will try to get to those questions during the content. That makes it far more relevant to the question to answer right then and there, rather than waiting to the end. And if you want a copy of today's slides, you can go ahead and just let us know. And we will get you a copy of the slides. You can do that in the feedback, or you can pop it into a question. And that is all for housekeeping. So without further ado, I'd like to hand it over to Christopher for our topic today. Christopher?
Sure. And actually, before we get to the topic, I've got a bit of a housekeeping as well. As Michael said, I do a number of meetups as well as webinars. I find myself in different places of the country when I go talk to customers on a fairly regular basis. And usually when I'm doing those, I try and see if I can attend or speak at meetups wherever I happen to be located. So if you're out there listening to this and you've got a meetup group that you think that you participate in, that you think would be interested in having me talk about Kubernetes, networking, security policy, Istio, or I don't know, motorcycle repair, feel free to let us know via the contact information as well, and we'll see if we can set something up for the next time I happen to be in the area. So with that, let's actually get on to the topic at hand. And the interesting thing, it's been a while since we've talked about this, and it's mainly services and DNS, and how do you expose services, and some changes that have been done recently in Kubernetes and with our product around DNS and service exposure. So it's been a while, and we still get this fairly common set of questions from our customer base, so I thought it'd be worthwhile to talk a little bit about today in the meetup, or webinar. So, so if we go to the first thing, so why are we talking about today? Kubernetes, is great. As we're coming up on Christmas time, right? My pods are deploying, my deployments are life cycling. It's all good. Everything's auto scaling. You just survived your Black Friday events, and everything's working great. But I've got these microservices, I've got these pods. How do I find and consume them within the cluster? And before we've talked about things like services, etc. So Kubernetes has got a services mechanism. We'll review that a little bit as well. But also, more importantly, how do I consume them from the outside? It's not all that useful if we're just talking to each other. So how do we consume these services and connect to these pods and microservices from the outside world? So without further ado, we're going to spend a little time talking about today. So next slide. Today we have two pods, and they need to talk to one another. Each of them has an IP address in Kubernetes, and they connect to them. We'll talk a little bit later about how we find those addresses, but pod B makes a connection to pod A. That's great. But what if we start scaling pod A? It's been life cycled, or it's auto scaling. We now have a bunch of pod A's. So how does pod B know which pod A or pod A's to connect to, and how do we load balance across that? How do we just keep updating pod B with all the new pod A addresses? That doesn't seem like a very scalable or modern architecture. So what Kubernetes gives you the ability to do is to define a virtual entity called a service. And in this case, service A represents the different pod A's that offer that service. And we'll show you the configuration for how that's done. But basically, we create this entity that says service A is a set of pods that all meet this set of criteria, in this case, pod A's. So service A is now this virtual container, and it points to all of the different pods in the cluster. So those pods we call endpoints. So now when you have a pod that's offering a service, it is an endpoint for that service. This is something that will resolve that service if there's a request for it. So how do we find this? First of all, we have to create service A, and that's created by a Kubernetes resource, and I'll show you that in a little bit. And when we do that, Kubernetes maps that service A to the endpoints that are offering it and creates a virtual IP, in this case 172.16.0.5. And that virtual IP is a proxy, if you want to think of it that way, for the service itself. So what then happens is there is some kind of mechanism, and there's different mechanisms in Kubernetes to do this, that will answer traffic for that virtual IP and then load balance it among the endpoints of the service. So pod B will discover, and we'll talk about that in a minute, that service A is at 172.16.0.5, and then by some networking magic, a load balancer will catch that traffic and load balance it between the various endpoints. One of those, there are couple of load balancers. One, you can use Istio. You could use kubeproxy, which is the standard Kubernetes mode. There are some others as well. But they're going to do that load balancing and distribute the traffic to the various endpoints based on some algorithm. So let's look at kubeproxy to begin with. So what kubeproxy is going to do is kubeproxy watches the definition of service A. So service A says made up of some number of endpoints. Kubernetes maintains that. Kubeproxy, which runs on each node independently, each worker node independently, is watching Kubernetes definition of service A and is keeping a list of all the endpoints that offer that service. So in this case, all those pod A's that we talked about before. And what kubeproxy does is kubeproxy programs IP tables in the underlying Linux host that basically does a load balance by doing a destination address NAT. So when a user requests or another pod requests traffic to service A, and sends traffic to service A's virtual IP on the host that they're originating the traffic from. What's going to happen is IP tables on that host is going to see the outgoing traffic addressed to the service's IP and will rewrite the destination IP to one of the endpoints that's currently offering the service. And then the network will transmit that traffic to that pod. So basically what we're doing is at the point of ingress, the first point where the fabric touches the packet that's destined for service A, we rewrite the source address, the destination address, to point it at one of the endpoints, and then standard networking takes over. That is, today, that's IP tables, and going forward in Kubernetes, IPVS is an option as well. It will become the default over time. So instead of using IP tables, it will be using another filtering mechanism in the kernel called IPVS. Slightly more performant, cleaner, and that support is coming. So, as a sort of a summary, Kubernetes services provide a logical service abstraction for a set of endpoints. It's implemented via kube proxy. A long time ago, it was actually user space proxy, and it's now IP tables and going to IPVS. Kubernetes functions fairly seamlessly, actually very seamlessly with kube proxy. We do not, many SDNs do require you to replace kube proxy. We operate with the existing kube proxy. And let's walk through a little bit of how this happens. So if you go to the next slide, there's a couple different ways of defining a service. You can create a YAML file that describes the service, or you can just use something called kubectl expose, kubectl expose. And basically what you're saying is you're going to take a deployment. In this case, the deployment is an Nginx deployment, and you're within the namespace, within a given namespace, Project Pink in this case, you are going to expose that deployment on port 80. So what's going to happen is now Kubernetes is going to create a service for Nginx in Project Pink namespace, and it's going to expose it on port 80. So any pod that happens to be within the deployment Nginx will now be exposed as an Nginx service. So what's going to happen is when that's done, kube proxy on each node, including on the masters, not just the workers, is going to see that the Nginx service has been created, and it's been given an IP address by Kubernetes, and it will then it will collect the pods that are serving Nginx right now, the Nginx pods from the deployment, and write those rules as NAT rules into the underlying host kernel identified by N on these boxes. So each node's kube proxy is going to write those rules independently on that host. So what's going to happen then is when a given pod tries to connect to the IP address for the service Nginx, it's going to be an IP address. If you're running Calico, it's going to be routed on the node, or Tigera, it's going to be routed on the node. If you're using some other SDN, it will somehow get to the underlying node from the pod, at which point the IP tables will pick it up, change the destination address of that packet from the service IP, which doesn't really exist as a network entity, it's just a placeholder IP, and will rewrite it to the IP address of one of the serving nodes, in this case IPv3, which happens to be on another host. Could be on the same host, could be on a different host, doesn't matter. And then standard networking, routing, etc. will happen and send that traffic to the destination pod, and the service will be delivered. So how do we discover those service IPs? So in Kubernetes, when we use DNS as service discovery. It's sort of the industry standard. It's what we've used for service discovery for decades in IP networks. So today, DNS in Kubernetes, until very recently, the default DNS provider in Kubernetes is something called kubedns. I need to rewrite this slide because as of last release, Core DNS is the new DNS provider, although you can still use kubedns, but there's a DNS provider that Kubernetes works with. When you define a service in Kubernetes, Kubernetes will send that service creation event to the DNS infrastructure within Kubernetes, and a DNS name will be generated. So if you create a service like we just did, Nginx, in namespace Project Pink, and we give it a virtual IP, service IP of 172.16.0.5, a DNS record will be created within Kubernetes that says nginx.projectpink.service.cluster.local is at 172.16.0.5. You can also have pods get IP addresses as well, but that's how DNS gets created. So whenever you create a service, the service's name will be created as a record in DNS within a subdomain for the cluster where that subdomain is the namespace. If you did not define a namespace for your service, it would be in the default namespace. So instead of Project Pink, it would be nginx.default.service.cluster.local. So that's how we find a service IP. You then use service names as long-lived names, and then in your applications, configuration, you say I need to connect to nginx.default service.cluster.local or nginx, and you will resolve that name within the Kubernetes cluster to whatever locally in Kubernetes is offering the nginx service. So what's going to happen, this is just another way of creating a service rather than the expose. In this case, we're creating a YAML file, the type service, and the name of the service is going to be web server, and it's going to be in Project Red namespace this time. And the selector is, we're going to select for any pods that have the two key value pairs of name is equal to nginx and tier is equal to front end. Cluster IP is where we could say this is the IP we want this to have. If we say none, it will get automatically picked. We'll pick an IP address. So in this case, when you do this, again, the DNS name for this would be webserver.projectred.service.cluster.local. When that happens, if we don't have a name server in Project Red yet, what's going to happen is Kubernetes will stand up an instance of the DNS server in Project Red. It'll be running as a pod somewhere in the network in Project Red's namespace. So in this case, that will be on IPA2 is the DNS server now for Project Red. The way resolution works, by default, Kubernetes will use, in the pod, you'll find an etcresolve.conf, which is a way of configuring how you resolve names within a Unix host or a container. And the entries will be they will first look for, a name, web server, for example, in that pod's namespace.service.cluster.local, then in default.service.cluster.local, and then whatever other things you've told it to look in, like your corporate DNS hierarchy. So if web server doesn't exist in Project Red, the next thing we'd try is resolve web server in default. That means, for example, if you want to have services that are shared commonly across multiple namespaces, you may want to put them in the default namespace, or you may want to put them in another namespace and then add that as a part of the config to the resolve.conf that gets fed to pods. And that's a DNS config in Kubernetes. So you can say I want to search for global services.service.cluster.local as one of the domains, and then put services in the global services namespace. So anyway, that's a little bit of how DNS works. Now let's talk a little bit. Before I go on, I do want to talk about another capability that we have added in Calico 3.4 for services. So in Calico 3.4, we now have the capability of BGP announcing service addresses. So for those of you who know about Calico, if Calico is running on private cloud, we use BGP to connect the pods and the Kubernetes cluster to the rest of your infrastructure. But to date, the only thing we announced was the pods IP addresses. We did not announce the services addresses. Starting with Calico 3.4, we have an ability to announce those service addresses via BGP. And we can do that one of two ways. We can either announce the service address. So let's say we go back and we have those 5 pods offering service A, and those 5 pods are running on 5 different hosts. If you define the service as a local service, then only those 5 hosts hosting pod A at that point in time would announce service A's IP address. If you have it set as a cluster-wide model for that service, then every node in your service will announce service A's IP address via DNS, via BGP. So you can control who announces it, but by turning a knob now in Calico 3.4, you can enable service address announcement via BGP. And we're going to continue to add capabilities around this space in forthcoming releases. So you now can physically expose your service IPs outside of your Kubernetes cluster directly. Let's talk a little bit about DNS. And so I just alluded to the fact that Core DNS is now the new DNS provider in Kubernetes, the new default as of 1.12. You can still use the legacy KubeDNS. The reason that we did this is that the KubeDNS, we as in the community, KubeDNS was built on a sort of older technology base, and it didn't have a lot of capabilities, expandability, and it wasn't necessarily the most robust DNS server in the world. So the Core DNS team took a very well-respected server called Caddy, which started off life as a Go-based HTTP server, and said, you know, we can make a really cool DNS server out of this infrastructure. It's very scalable, very extendable, etc. So they basically took the Caddy base and flipped it over into being a DNS server, and that became called Core DNS. It's a CNCF project now. Very extensible and pluggable. Durable as well. I mean, from the get-go, Caddy was designed to be a server that faced the public internet and therefore fairly robust in face of attacks and hostile environments. So, whereas before I never would have counseled somebody to expose a KubeDNS server to the outside world, a Core DNS server I think is perfectly fine to expose to the outside world. And it's extensible. There's lots of things we can plug into Core DNS. There's lots of capabilities and features that we can plug in. So, let's talk about some of those. One, you know, this is a drop-in replacement for KubeDNS. We can rewrite DNS rules. So we can rewrite DNS entries, and I'll show you that in a minute. You can also configure it to trade off memory usage for external resolution time. So if you're resolving DNS queries, external DNS queries in KubeDNS and in Core DNS, that can take some time. We'll talk about that in a couple of minutes, but it's very memory efficient. You can say you want to be a little less memory efficient, but you want the resolver times to be shorter, and you can configure that, and we'll talk about that in a minute. Also, external Core DNS servers can be connected to one or more Kubernetes clusters and namespaces. So this becomes interesting when you have services in KubeDNS and in Kubernetes. They want to expose the rest of your organization, or even broader than that. What you can do is have, you know, within Kubernetes, obviously you have your DNS servers, your Core DNS servers are running and resolving answers coming from within the cluster, but how do things outside of your cluster resolve those names? So you can actually run Core DNS servers as just regular DNS servers, like any other DNS server in your organization, and point to them via your DNS route in your organization and delegate domains to them. And then those domains can be wired into different Kubernetes clusters and namespaces. So you can actually have a Core DNS server that is going to answer queries for Kubernetes resources just as if it was in the Kubernetes cluster itself. In fact, it's getting the data from the same place as the in-cluster DNS servers. Everything's going back to the Kubernetes API server or to etcd. So it's going to behave just like a Kubernetes DNS server. It's just going to be exposed outside of the cluster. So that's what now gives you a very easy way of surfacing resources within Kubernetes on a DNS basis to things outside of the cluster itself. If we go to I was talking about Core DNS Autopath. This is a feature where you can adjust the trade-off between memory and resolution time. If you don't have this Autopath feature turned on, DNS answers for zone entries or DNS entries within the cluster take about 2 milliseconds. If you try and resolve something outside of the cluster, it can take up to 12 milliseconds. But you'll be using less than 200 megabytes per Core DNS image to do that. Your memory structure will be fairly small, even in very large clusters where you have 150,000 or more pods and services. If you don't like that six-fold increase in time between internal and resolving, cluster.local versus google.com. You can turn on Autopath, and what that's going to do is that's going to keep all resolutions down to about 2 milliseconds. So everything will resolve in 2 milliseconds now, give or take. But you are going to have an increase in memory utilization, a little bit over double the amount of memory utilized, because it's going to be doing a lot more caching, and there's some other things it's going to be doing in parallel, but you're going to be using more memory in order to get that performance. And now you can trade off. Do you want your core DNS servers in your cluster to be using more memory and responding faster, or responding a bit slower? The next thing you can do is you can do DNS rewrites. So there's a whole bunch of things here. I encourage you, if you're interested in doing this, looking at the core DNS documentation. But you can do things like replace suffixes in domain names. In the second example there, rewrite name suffix schmoogle.com to .google.com, and you create a schmoogle.com zone in core DNS, and then somebody tries to resolve www.schmoogle.com. Core DNS will rewrite that to www.google.com and then resolve that. So you can now start using this to swap out names from, say, a Kubernetes name to a more externally friendly name to expose those services to the rest of your estate. Similarly, you can even use regexes to regular expressions to rewrite these in a more programmatic fashion. So, in this case, anything.uswest1.example.org is going to get rewritten to anything.service.uswest1.console. So if you're using console as a name resolution service or as a service discovery service, you can map those console names into a corporate name. So core DNS gives you a lot of capabilities. There's a lot more than just that, but those are some of the high points. The last thing I want to talk about is external DNS. So external DNS is a service. It is an incubator project within Kubernetes. I would not use it yet in production, but if it's something of interest, I'd play around with it. The API is not static at this point. It's still an incubator project. The API might change. But what this allows you to do is attach an annotation to a Kubernetes pod that says, I want this pod or this service to have a specific name. So in this case, I want my Nginx pod, which, if you'll remember as a service, would be nginx.whatever namespace.service.cluster.local. It will still get that, but it will also be given a name of nginx.example.org. Including AWS Route 53, including Google DNS, DigitalOcean. There's a number of name servers that it works with. What's going to happen whenever we grant a service IP to a given service, where that service definition has this annotation, we will then, what external DNS does then is updates. You configure external DNS with what name servers are supposed to manipulate, and it's the credentials that would need to do so, and then external DNS will plop in a record, an A record or a quad A record, for a given service, in this case nginx.example.org, into the example.org name servers. And if it has the right permissions, that's successful. So for example, if you're on AWS, it could update your example.org Route 53 records, or your Google Cloud DNS records, or if you're on-prem private cloud and you're running core DNS, it can update your core DNS server that's hosting example.org. So this now gives you the ability of assigning directly external DNS names. So you can now surface external DNS names for your services using external DNS or core DNS, rewrite rules, or a combination of the two. So there's a number of interesting things you can now start doing with DNS to make it easier to expose and consume your Kubernetes resources outside of the cluster. And with that, I will take questions, but I think that's about the end of my little quick tour through Kubernetes services, BGP announcements of services, and DNS.
Yep. Thanks, Christopher. Yeah, so we're going to be fielding questions now, but just as an update, the next Tigera webinar is coming up in January. The link is there, and the topic is, so this was our first in what we're calling the Kubernetes Learning Series. It's about, topics that are important about Kubernetes that aren't necessarily related, but they aren't necessarily on security and compliance, the core things that Tigera and Calico do. So the next one coming up is based on Kubernetes ingress and egress traffic management, and that's coming up in January. So there's the link if you want to go ahead and register, attend. Because you attended this webinar, you don't have to fill out a form. All you have to do is just say you're going to attend it, and it's all set. Really easy. So, Christopher, I know that this content was a little packed, with information. I think we don't have any questions, so either it was also complete and everyone is great.
Or they're all asleep.
Or they're all asleep. No, they're not asleep, for sure. They're probably all now looking at their DNS setup and wondering what the heck is going on. Why aren't they setting it up correctly? So a copy of the presentation will be made available to you by email. We'll send a thank you email from us and have a link to that. So if you want to review this content. But once again, like I said, as soon as we end this webcast in a minute, it's going to be available on the Bright Talk Network, recorded in about 5 minutes. Okay. So without further ado, with no questions to answer, I'd like to thank you all for attending, and we will see you next time. Okay. Bye.